Sweetness is a sensory illusion built on molecular recognition. Whether derived from plants, peptides, or synthetic scaffolds, every sweetener activates the same TASR1, TASR2 receptor complex, and many chemists over the years have learned ways to gaslight your taste buds into thinking something is sugar when it's actually not. Sweetness happens when certain molecules fit into the TAS1R2, TAS1R3 receptor complex on your tongue. This receptor detects the shape and charge pattern of sugars and sweeteners. When a match to these receptors is found, it triggers a G protein signal cascade, opening ion channels and sending an electrical signal to your brain that says, sweet. Sucrose, better known as table sugar, is the natural benchmark for sweetness and the molecular standard to which all sweeteners are compared. It's a disaccharide of glucose and fructose linked via an alpha-1,2 glycosidic bond. Naturally abundant in sugarcane and sugar beet, sucrose is metabolized by sucrase into its monosaccharide components, which enter glycolysis and contribute about 4 kilocalories per gram. Sucrose melts at 186 degrees C and caramelizes upon further heating, producing the desirable Maillard reaction seen in cooking and baking. Beyond its caloric role, sucrose contributes to texture, osmotic stability, and microbial preservation in foods. Industrially, sucrose's structure provided the template for designing synthetic analogs like sucralose and Neohesperidin dihydrochalcone, allowing scientists to explore how subtle modifications, halogenation, glycoside rearrangements, or functional group substitutions affect the binding to the TAS1R2, TAS1R3 receptor. It remains both a chemical reference point and a metabolic fuel central to human nutrition. Its sweetness intensity is assigned as the value 1.0 by convention. Saccharin, the oldest artificial sweetener, was discovered accidentally in 1879 by Konstantin Fallberg at Johns Hopkins University during coal tar derivative research. Chemically, it's 1,2-benzisothiazolone 3,1,1,1 dioxide, or O-sulfobenzamide. It can range 300 to 700 times the sweetness of glucose, with a pronounced bitter or metallic aftertaste at high concentrations. Saccharin's small rigid structure allows it to act as a non-caloric sweetener since it's not metabolized and is excreted unchanged in the kidneys. It's stable under heat and across wide pH ranges, and ideal for shelf-stable products. In the 1970s, rodent studies had linked saccharin to bladder tumors, leading to a temporary ban and mandatory warning labels. Later research determined the effect was specific to male rat physiology and not relevant to humans, and the warnings were removed by the year 2000. Saccharin remains approved worldwide as E954, commonly used in diet sodas, tabletop sweeteners, and pharmaceuticals. Cyclamate was discovered in 1937 by graduate student Michael Sveda at the University of Illinois. It's the sodium or calcium salt of cyclohexylsulfamic acid, about 30 times sweeter than sucrose. Its sweetness is considered mild with a slow onset and clean finish, often used synergistically with saccharin to mask each other's off notes. Cyclamate's thermal and pH stability make it suitable for processed foods and beverages. In the body, some gut bacteria converted to cyclohexamine, which prompted toxicological concerns in the late 1960s. After studies in rats suggested possible bladder carcinogenicity, the FDA banned cyclamate in 1970, though it remains approved in over 130 countries, including the EU and Canada, where further evaluations found no carcinogenic risk at dietary exposure levels. It remains valuable as a model in sweetener structure activity research due to its small, rigid sulfamate scaffold that interacts differently with sweet taste receptors than peptides or carbohydrate-based sweeteners. Sucralose was discovered in 1976 at Queen Elizabeth College in London when researchers at Tate & Lyle and King's College were modifying sucrose molecules to create chlorinated derivatives. Graduate student Shashikant Fondas reportedly misheard test as taste, leading to the accidental discovery of its sweetness. Chemically, sucralose is 1,6-dichloro-1,6-di-dioxy-beta-D-fructofuranozoyl 4-chloro-4-deoxy-alpha-D galactopyranoside, produced by selective chlorination of sucrose's hydroxyl groups. This modification prevents enzymatic hydrolysis, making sucralose non-caloric and non-metabolizable. It's approximately 600 times sweeter than sucrose, with a sweetness profile nearly identical to sugar, but with longer persistence and slightly cooling notes. Sucralose is highly heat-stable, soluble, and pH-tolerant, enabling use in baked goods, beverages, and pharmaceuticals. After ingestion, about 85% is excreted unchanged, and the rest is minimally metabolized. Approved by the FDA in 1998 and globally as E955, it's a benchmark chlorinated carbohydrate sweetener that bridges carbohydrate chemistry and synthetic taste receptor design. Discovered in 1976 by Carl Klaus at Host AG, acesulfame potassium, or ACE-K, emerged accidentally during sulfonamide research. Chemically, it's the potassium salt of 6-methyl-1,2,3-oxythiazine 4,3-H1,2,2 dioxide. The cyclic sulfonamide derivative contains a sulfonamide group critical for its sweetness profile. At about 200 times sweeter than sucrose, ACE-K is heat stable, making it ideal for baked goods and beverages. It's non-metabolized in humans, excreted unchanged in the kidneys, and provides no calories. Often blended with aspartame or sucralose, it synergistically masks bitter aftertastes and enhances the sweetness onset. Despite its stability, ACE-K's slightly bitter metallic undertone has led to its pairing with other sweeteners in commercial formulations like Coca-Cola Zero and sugar-free gum. Its approval history began in Europe in 1983 and in the US by the FDA in 1988 for general use. Discovered in 1965 by James Schlatter at GD Searle while synthesizing the anti-ulcer compound, aspartame is a methyl ester dipeptide composed of L-aspartic acid and L-phenylalanine. It's about 180 to 200 times sweeter than sucrose. Its sweetness arises from the interaction of its carboxylate and amide groups with the TAS1R2, TAS1R3 receptor, producing a sucrose-like profile with slower onset and lingering sweetness. Chemically, it's unstable at high temperatures and low pH, undergoing hydrolysis and cyclization to form diketopiperazine. This is a major limitation in baked goods and acidic beverages. Aspartame metabolizes into aspartate, methanol, and phenylalanine, giving it a caloric value of roughly 4 kilocalories per gram, though used in tiny amounts. It is not recommended for individuals with phenylketonuria. Marketed as NutraSweet and Equal, it became one of the most widely studied and debated artificial sweeteners, with safety reaffirmed by the FDA, EFSA, and WHO. Its discovery marked a major step in peptide-based sweetener design, bridging food chemistry and taste receptor biophysics. Alitame was developed by Pfizer in 1980 as a dipeptide sweetener related to aspartame, but incorporating an L-aspartic acid and D-alanine amide linked to a thiazolidine. Its chemical name, L-alpha-aspartyl N2244 tetramethylthiazolidine 4-carbonyl D-alaninamide, gives a clue to its structural complexity. Alitame is about 2,000 times sweeter than sucrose, with a clean, rapid sweetness onset and no bitter aftertaste. Unlike aspartame, it is stable under heat and across pH ranges, enabling use in baked goods and processed foods. Pfizer sought global approval under the brand name Acclaim, but despite approval in several countries, it was never approved by the FDA due to insufficient toxicological data submission. It was ultimately licensed to Danisco, but limited global market demand and high production costs curtailed its commercial expansion. However, Alitame remains a benchmark molecule in the study of peptide-based sweeteners with improved thermal stability. Neotame is a second-generation dipeptide sweetener developed by Ajinomoto in the 1990s as an improvement on aspartame. Structurally, it's an N33-dimethylbutyl L-alpha-aspartyl L-phenylalanine 1-methyl ester, incorporating a bulky tertiary butyl group on the aspartyl nitrogen that protects it from enzymatic hydrolysis. This modification dramatically increases stability and sweetness potency, 7,000 to 13,000 times sweeter than sucrose, while also eliminating the bitter and metallic aftertaste typical of other high-intensity sweeteners. Neotame is heat and pH stable, suitable for baking in acidic beverages, and metabolized minimally, producing trace phenylalanine far below phenylketonuria concern thresholds. It was approved by the FDA in 2002 and globally thereafter. Because of its extreme sweetness, it's typically used in microgram quantities, often blended with bulk sweeteners to mimic sucrose temporal profile. Its structure-activity relationship studies have contributed significantly to mapping the binding pockets of TAS1R2, TAS1R3, and the conformational flexibility that defines human sweet taste perception. Neohesperidin dihydrochalcone, or NHDC, is a hydrogenated flavonoid derivative synthesized from neohesperidin. a compound found in bitter oranges. It was developed in the 1960s by the U.S. Department of Agriculture during efforts to debitter citrus juices. NHDC is about 1,500 to 1,800 times sweeter than sucrose and exhibits a cool, lingering sweetness with a licorice-like aftertaste. Its structure features a dihydrochalcone backbone with multiple hydroxyl and methoxy groups that interact strongly with TAS1R2 and TAS1R3 receptor complexes. It's stable under heat and in acidic environments, making it suitable for beverages, chewing gum, and pharmaceuticals, where sweetness masking is needed. NHDC's low bitterness threshold allows it to function as a flavor enhancer, modifying the perception of other sweeteners or reducing the harshness in caffeine-containing products. It's approved in the European Union as E959 and widely used in formulations where long-lasting sweetness is desired. Glycyrrhizin, the principal sweet component of licorice root, or Glycyrrhiza glabra, was first isolated in 1933. It's a triterpenoid sapon and glycoside consisting of glycyrrhetinic acid bound to 2 glucuronic acid units. Its sweetness potency is roughly 30 to 50 times that of sucrose, with a distinctive licorice-like flavor and delayed onset. Glycyrrhizin's amphiphilic structure allows it to foam in aqueous solutions, making useful for beverages and also in traditional herbal formulations. In metabolism, intestinal bacteria hydrolyze it to glycyrrhetinic acid, which inhibits 11-beta-hydroxysteroid dehydrogenase, leading to pseudoaldosteronism in high doses, a condition causing sodium retention and hypertension. Because of this, regulatory limits exist on its use as a sweetener. Beyond flavoring, glycyrrhizin is studied for anti-inflammatory and antiviral properties, including modulation of tumor necrosis factor alpha and interferon pathways. Commercially, it remains popular in Asian confectionery and pharmaceuticals, offering a natural yet pharmacologically active sweetness profile. Steviosides are glycosides extracted from Stevia rebaudiana, a plant native to Paraguay and Brazil. These diterpene glycosides, on average, are 30 times sweeter than sucrose, but can range up to 300 times sweeter than sucrose, and consist of a steviol acylcone attached to several glucose units via ester and glycosidic bonds. The sweetness arises from the hydrophilic sugar moieties interacting with TAS1R2, TAS1R3 receptor binding sites, while the hydrophobic diterpene core contributes to a delayed lingering profile and mild bitterness. First commercialized in Japan in the 1970s, steviol glycosides gained global acceptance as natural non-caloric sweeteners. They're heat and pH stable, used in beverages, tabletop products, and baking. In metabolism, they're hydrolyzed to steviol by gut microbiota, excreted largely unchanged, contributing no caloric energy. Safety evaluations by JECFA and the FDA confirm non-toxicity at realistic consumption levels. Mogrosides are natural triterpene glycosides isolated from the fruit Serratia grosvenori, commonly called the monk fruit or lao han guo. First characterized in the 1940s, the main sweet constituent is Mogroside 5, a cucurbitane-type aglycone known as a Mogrol linked to multiple glucose units. Mogrosides are 150 to 300 times sweeter than sucrose, with a sweetness profile that's considered clean but with a slight lingering note due to the slow receptor dissociation. Being heat and pH stable, they're used as natural non-caloric sweeteners in foods and beverages. Unlike synthetic sweeteners, Mogrosides are metabolized to Mogrol and glucose but are poorly absorbed, contributing negligible calories. They're generally recognized as safe by the FDA and widely used in Asia since traditional Chinese medicine employed the fruit for its anti-inflammatory and antioxidant effects. Commercial extracts standardize Mogroside 5 content for consistent sweetness and are often combined with erythritol to improve mouthfeel and reduce aftertaste. Thaumatin is a natural sweet-tasting protein first isolated in 1972 from the fruit of the West African plant Thaumatococcus danieli. It's a mixture of intensely sweet proteins, primarily thaumatin 1 and 2, composed of about 207 amino acids stabilized by 8 disulfide bridges. Thaumatin is approximately 1,600 to 3,000 times sweeter than sucrose on a weight basis, but its sweetness develops slowly and lingers, producing a licorice-like aftertaste. Structurally, its sweetness derives from specific surface-charged regions that interact electrostatically with the TAS1R2, TAS1R3 receptor complex, quite distinct from the small molecule mechanisms of synthetic sweeteners. Thaumatin is heat stable under mildly acidic conditions, but denatures under strong heat or alkaline pH. It's metabolized as a normal protein, yielding amino acids with negligible caloric contribution at practical use levels. Approved in the EU as E957, it's employed in chewing gums, flavor masking agents, and low-caloric foods. Lugduname was first synthesized in 1996 at the University of Lyon. Lugduname in Latin, hence its name. It was synthesized by a team led by Felipe Norfre and Daniel Tinti. It's part of a family of guanidine derivatives designed to probe the structure-activity relationships of sweet taste receptors. Structurally, it contains an N4-cyanophenylguanidine moiety connected through a urea linkage to an oxythiazanone dioxide ring, combining motifs for both sulfamate and amidine-based sweeteners. Lugduname's reported sweetness intensity is 200,000 to 300,000 times that of sucrose, making it one of the most potent synthetic sweeteners known. It has never been commercialized, mainly due to complex synthesis routes, limited toxicological data, and unpredictable receptor overactivation at high potencies. Lugduname remains primarily a laboratory benchmark used to map the extreme sensitivity limits of human sweet taste perception.